In the previous lecture, we started studying about threats, and we saw the difference between single-threaded processes and multi-threaded processes, and we also saw the benefits of multi-threading. So in this lecture, we'll be studying about multi-threading models and hyperthreading. So before we go into multi-feeding models, let us understand the type of threats that we have. So basically, there are two types of threats. The first one is user threats, and the second one is kernel threats. So user threats are the threats that are supported above the kernel and are managed without the kernel support. So these are the threats that are operating in user level, or which are created by the users or the developers. And then we have the kernel threats. So the kernel threads are supported and managed directly by the operating system. So kernel threads are the threads which are managed directly by the operating system and not by the user. So these are the two types of threats that we have. So when we started studying about operating system, we saw that the users are constantly interacting with the system, and operating system is what allows this to happen. So since we have seen that there are two types of threats, the user threats and kernel threats, so for these two threats to be able to function together, there must exist a relationship between the user threat and kernel threat. So ultimately, for the system to function, there must exist a relationship between the user threats and the kernel threats. So we will see how we can establish this relationship between the user threats and the counter threats. So that is the thing that we are going to study in multi-threading models. So multi-threading models are nothing but the type of relationships that can be there between the user threats and counter threats. So we will see what they are. So there are three common ways of establishing this relationship. And what is this relationship? The relationship between user threat and the counter threats. So let's see what they are. The first one is many-to-one model. The second one is one-to-one model. And the third one is many-to-many model. So we will see each of these models one by one, and we will see how do they function, what are their limitations, and which one among these are the best. So coming to the first model, we have the many-to-one model. So from the name itself, we can understand that there is a many-to-one relationship established between the user threat and the kernel threat. So from this diagram, we can see these things on top. They represent the user threats. And then the circle over here, it represents the kernel thread. So we see that many user threats are associated to one kernel thread, or many user threats are accessing one kernel thread. So that is what we mean by the many-to-one model. Many user threats to one kernel thread. So as I told you, in this model, it maps many user-level threats to one kernel thread. And then the threat management is done by the threat library in user space. So it is efficient. Threat management is done in the user level, not in the corner level. So in that way, this is efficient because we are able to manage the threats in the user space. Now let us see the disadvantages or the limitations of this model. So here are the limitations. The entire process will block if a threat makes a blocking system call. So we see that many user threats are associated or mapped to one corner thread. And if one of the thread makes a blocking system call, then the entire process will be blocked because let's say that all these threats are associated to one single process. They are the threats of one single process doing a certain task. And all these threats are mapped to this kernel thread in the operating system. So let's say that one of the threat makes a blocking system call. So if that threat makes a blocking system call, this kernel thread will be blocked. And if this is blocked, then all of them will be blocked because they are all mapped to this single kernel threat. So that is one of the limitations or disadvantage of this model. So if one threat makes a blocking system call, the entire process will be blocked. And then the second limitation is that because only one thread can access the kernel at a time, multiple threads are unable to run in parallel on a multiprocessor. So as you see here, since this multiple threads in the user level are mapped to just one corner thread, even if we are having a multiple processor system, if you are having a multiprocessor, we are not going to be able to make use of the multiprocessor system because even though we have multiprocessor, that means even though we have more than one processor, one kernel thread will run only in one of the processor. One kernel thread cannot run two processors. So even though we have many processors, this entire thing will run only in one of the processors because they are all mapped to one kernel thread. And one kernel thread will run only one of the processor. So that is another limitation of the many-to-one model. Alright, so now let's go to the next model and see how is that better than this, and if that has any limitations as well. So the second model that we have is one-to-one model. So from the name itself, even here we can understand here that one user thread is mapped to exactly one kernel thread. Unlike the many two-one model here, one user thread is mapped to only one kernel thread. So here, this user thread is mapped to this kernel thread, this one to this one, and so on. So let us see how does this work, and what are its benefits, and what are its limitations. So as I told you, in this model, it maps each user thread to one kernel thread, and then it provides more concurrency than the many-to-one model by allowing another thread to run when a thread makes a blocking system call. So in this case, even if one user thread makes a blocking system call, the entire process will not be affected, unlike the many-to-one model. So here let's say, for example, that these four threads belongs to one process, and then let's say that one of the user thread makes a blocking system call. So if it does so, only this kernel thread associated with this user thread will be affected, and only this part will be blocked. So the other part of the process, that means these three threads are suited with these three kernel threads, can still run, even though this had made a blocking system call. So that is one advantage as compared to the many-to-one model. And also it allows multiple threads to run in parallel on a multiprocessor. So in the previous one, we saw that we cannot make use of the multiprocessor system. But in this case, we are able to make use of multiprocessor system. Why? Because each user thread is associated to one kernel thread. So each of this part can run on one of the processors that we have. So suppose we are having four processors in our system. Then each of these threads can run on one of the four processors. So this one can run on one, this on another one, and so on. So we are able to make use of the multiprocessor architecture that we have in case of the one-to-one model. So far we saw that one-to-one model is having some advantages as compared to the many-to-one model. Now let's see if it has some disadvantages, and if they have, what are they? So here are the disadvantages. Creating a user thread requires creating the corresponding kernel thread. So here we see that each user thread is mapped to one kernel thread. So whenever you are creating a user thread, you have to create the kernel thread as well. So that may become costly sometimes. And because the overhead of creating kernel threads can burden the performance of an application, most implementations of this model restrict the number of threads supported by the system. So the overhead of creating kernel threads can sometimes be very heavy on the system or the application that is running. So what happens is that most of the applications, they will restrict the number of kernel threads that can be created, because in one system there is a limit of how many threads can run at a time. So if you are having a multi-processor system with four processors, then at a time only four threads can run, because each thread will run on one of the processor. So if you are having a processor with 4 cores, that means you're having 4 processors your system. And if you having are 5 threads and trying to make those 5 threads run at the same time, it may not work. So the obligation may have to restrict the number of threads that are supported. So that is another disadvantage of this one-to-one model. Now let us go to the next model and see if that is better than this two that we have discussed till now. So here we come to the last model, which is a many-to-many model. So here again, from the name, we can understand that many user threads are associated or mapped to many kernel threads. So from the diagram, it is very clear. Here we have the user threads, and here we have the kernel threads. And these user threads are associated with this corner threads, or they are mapped to this corner thread. So there is so many-to-many relationship in this model. So let us see what are the advantages of this model, and if this is better than the other two that we have discussed. So here, as I told you, in this model, it multiplexes many user-level threads to a smaller or equal number of kernel threads. So as we see here, there is a mapping between many user-level threads to a smaller or equal number of kernel threads. So here, we have 4 user threads, and they may be mapped to 4 or lesser number of kernel threads. That is what we mean by this. And then the number of kernel threads may be specific to either a particular application or a particular machine. So as I told you, there is a limitation of the number of threads that we can have in a system. So the number of kernel threads that we can have in this model, it may be specific to a particular application or a particular machine, depending upon the number of threads that they support. And in this one, developers can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on a multiprocessor. So here, as we see, the developers can create as many number of user threads as they want, and they will be mapped to the corresponding number of kernel threads, and they can run in parallel on a multiprocessor. So we have talked about how threads function in a multiprocessor system, so we can clearly see that in this they can run on a multiprocessor system because we are having multiple kernel threads. And also, when a thread performs a blocking system call, the kernel can schedule another thread for execution. Here we see that when our user thread performs a blocking system call, the entire process will not be blocked. The remaining things can be scheduled for execution when one user thread performs a blocking system call. So these were the limitations that we had in the many-to-one model and one-to-one model. When many-to-one model, we saw that when a blocking system call performed, the entire process blocked, but that problem is solved in many-to-many model. It was also solved in one-to-one model, but in one-to-one model there were other problems that we faced, like user thread could be associated mapped or only one corner thread, but in this one there is a many-to-many relationship. So in that way, also many-to-many model is better than the one-to-one model. So we see that this many-to-many model, it is having many advantages, and it is far better than the many-to-one model and one-to-one model. So this is the model that is implemented in most systems, and this is the best model that we can have in a multi-threading system to establish a relationship between the user thread and the kernel threads. Now we will discuss another topic, that is hyperthreading, which is also known as simultaneous multi-threading. So we have been studying about multi-threading, and we saw how multi-threading is much better than a single threaded process. We saw its benefits, and we also saw the morals in which the relationship between user threads and threads are established in a multi-threading system. So what we mean by simultaneous multi-threading is that we are having more than one multi-threading going on in the same system. Multi-threading means multiple threads at the same time, and simultaneous multi-threading means many of this multi-threading going on at the same time. So that is what simultaneous multi-threading is, and hyperthreading is the same thing. It is just the proprietary name given by Intel. So Intel company, they call it hyperthreading. So let us see what is the advantage of hyperthreading or simultaneous multi-threading and how it actually works. What happens is that in a hyper-threaded system, it allows their processors' cores resources to become multiple logical processors for performance. So what we have is we are having a microprocessor. That means we are having a processor in our system where all the processing is happening. And in our processors, we are having different cores, right? We have heard of single core systems, dual core systems, quad core systems, and so on. What happens if it is a single core system? That means there is only one processor where only one processing can take place at a time. That means only one thread can run at a time. And if we are having a dual core processor, that means in your processor you are having two cores where two processings can happen at the same time. That means it will support two threads at the same time. So in the same quad core means 4 cores, so 4 units of processing. That means 4 threads can be supported at the same time. So physically, depending upon the number of cores you have, that many number of threads it will support at one time. So in this hyper-threading or simultaneous multi-threading, what happens is that the physical cores of your processors, they are virtually or illogically divided into multiple processors. So if you having one core, it may be logically divided into two. Physically, it is only one, but logically, it may be divided into so that two threads may be supported at the same time. Similarly, you are having a dual core system, then those two cores may be logically divided into each. So you will have a total of 4 cores where 4 different threads can run at the same time. So that is what we mean by simultaneous multi-threading or hyper-threading. So what happens? It enables the processors to execute 2 threads or a set of instructions at the same time. Since hyper-threading allows 2 streams to be executed in parallel, it is almost like having 2 separate processors working together. So this is what I explained to you. Now let us see, how can we find out if your system that you are using supports simultaneous multi-threading or hyper-threading? And let us see how we can find out if hyper-threading is running in our system, because it is always interesting to practically see what is happening instead of just learning the theory. So let us try to find out how this works. So here, I just want to show you the properties of the system that I'm using right now. So here, I am having a processor which is a Intel Core i3. and it belongs to the 2370 model. So this is the processor that I am having in my system right now. So in order to find out whether my system is hyper-threaded or not, what you have to do to open your command prompt. So you open up your command prompt, and here you type WMIC. So WMIC stands for Windows Management Instrumentation, which is a management infrastructure that provides you access to control over a system. So if you type WMIC, it will open up the Windows Management Instrumentation console. So if you press enter, you enter the command line interface of dummies. So here I will show you the command which will help us know how many cores are we having in our system. So here there is a command called CPU get number of cores. If you type this command, it will show you the number of cores that you have in your system. That means the number of cores in your processor. So we know there are different types of processors having different cores. And as I told you, if you are having multiple cores, means it is a multi-processor system. So here you see that I am having 2 cores in my system. That means there are 2 threads that can be supported at the same time. So it is just like having 2 processors. Now we will find out how many logical processors do I have. Now if the number of logical processors is equal to the number of physical cores, that means there is no hyper-threading happening in my system, because I am just having that many number of cores as a physical cores that I have. But if I'm having more number of logical cores as compared to the physical cores that we saw here, then that means hyper-threading is happening in our system. So in order to do that, there is another command. So let us extend this command. Here we said get number of cores. Now we will also say number of logical processors. Now if I press enter here, what do I see? I see that number of cores is 2, which we saw before, and number of logical processors is 4. So we see that physically we had only 2 cores, but they are divided into 2 each. And as a total, I am having 4 number of logical processors. So here we clearly see that there is hyper-threading. I am having 4 logical cores. That means I can run 4 threads at the same time in my system. So clearly my system is hyper-threaded. So that is how we can find out how many cores we have, and also we can find out if our system is hyper-threaded or not. So with that, I hope you understood the concept of hyper-threading. So this topic may not be present in your syllables or in your textbooks. But this is something good to know, because this is the kind of technology that we are using today. So we have seen the models of multi-threading, and we also saw hyper-threading and how it works in our system. Thank you for watching, and see you in the next one.